In today's lecture, we'll finish looking at exponential functions, and then we'll move on to logarithmic functions, which are the exact opposite of exponentials, and they cancel them out. So recall from our definition that if we have some function, f of x is equal to a to the power x, where a is greater than 0, but not equal to 1, we say that this is the exponential function with base a. We've also said that there are quite a few applications of exponentials, and the one we'll look at today involves figuring out compound interest over time. If we want to study compound interest, we need to look at a very special function that involves a very special number. And this is the number e. E is an irrational number, like pi, that we found by looking at compound interest. And e is about 2.71828, blah, blah, blah. For the most part, when we do calculations and we're not using our calculator, remembering it to be 2.718 is enough. E is a very nice number that arises in nature a lot when we look at exponential growth and exponential decay, population growth, population decay, and all sorts of things in between. The function is f of x is equal to e to the power x, and since it's an irrational number, we normally need a calculator or a computer to actually work with it. Now, how does this relate to compound interest? Well, to understand that, we'll need to understand what compound interest is. Compound interest is when we invest money and that accumulates interest. Then we take the interest and we sort of throw it back into the pot, and the interest starts to accumulate interest, which accumulates more and more and more. And so our interest is actually growing our money faster and faster. The formula for compound interest a certain number of times a year is the following. F is equal to P times 1 plus R divided by N to the power N times T. P is the principal, or how much money we invest. R is our annual percentage rate, the rate at which our money grows. T is our time in years, and we like to keep it in years to keep everything standard. And N is the number of times interest compounds per year. Now, N can be a couple things. It can be yearly, where our interest grows once a year, and we add it back in. It can be twice a year. It can be quarterly, 4 times a year. It could be monthly, or it could be daily, and anything in between. And since we allow ourselves to think about compounding interest faster and faster and faster, where we get interest every single day, the question arises, what if we took this to the extreme and we started accumulating interest continuously? The interest builds and builds and builds hundreds of times every second. We might think that our money should grow to infinity very, very quickly, but this doesn't turn out to be the case. Actually, as we allow compound interest to compound continuously, instead of some finite number per year, for example, instead of monthly, this formula converges very nicely to what we call the PERT formula, as you might guess. In this formula, P is still principal, R is still the annual percentage rate, and T is still time in years, but we don't have an N anymore since our interest is compounding literally as fast as possible. And it becomes an easier formula, and the rate at which our money grows stabilizes at this 2.718 number, which is very interesting and very easy to use. So let's see how we can plug some numbers into these formula and see what the money turns out to actually be. So let's say we invest $12,000 with an annual percentage rate of 3%. We would probably want to know how much money do we have after 5 years when the interest is compounded monthly. And then once we figure that out, we'll look to see how fast the interest accumulates if we allow it to do it continuously, so we can compare how fast the money's growing. For a finite number of compoundings per year, for example monthly, our formula is f is equal to p times 1 plus r over n to the power nt. We invest $12,000, so this is our principal, times 1 plus our annual percentage rate, 3%, which is 0.03, divided by the number of times compounded per year. Since this is monthly, it'll be 12 times. And then to the power, number of times compounded times year. 12 times 5 means that we will compound interest 60 times. When we put this into the calculator, we'll see that we have $13,939.40. So after 5 years, our $12,000 investment grew by about $2,000. Now what if we allowed it to compound continuously? Here we need to use our other formula. F is equal to P times e to the power RT, or PERT. And again, we plug in our numbers. P is 12,000. E is a nice irrational number. R is 0.03, 3%. And T is 5 years. When we plug this into our calculator, we'll see that we'll get $13,942.21. So allowing our interest to compound continuously does give us a little bit more money, but not as much as we might think. It actually stabilizes very quickly, and the number of times we compound per year is not nearly as important as what our APR is. So having a higher APR is normally a lot better than having more and more compounding. All right. So now that we understand exponentials well, let's look into another aspect of them. So remember that exponents are repeated multiplication. So let's look at simpler things like addition and multiplication to start finding some new questions about exponentials. So we defined subtraction to cancel out addition many, many years ago. And we had a way to, anytime we add, sort of undo it and get back to our original number x. Similarly, once we defined multiplication, we defined division to cancel it out. And so that we have, if we ever multiply by something, we have a nice way to move it to the other side and get rid of it. But now, how can we cancel out exponents? Or in other words, what is the inverse of the function f of x is equal to a to the power x? If we think about this off the top of our heads, we won't be able to find an answer very easily. And since this is the case, we actually make up a new function specifically to cancel out exponentials. So it's sort of like doing exponentials, but in reverse. So let's give this definition. For x greater than 0, a greater than 0, and still a not equal to 1, we say the function f of x is equal to log base a of x is called the logarithmic function with base a. Just like before, when we had an exponent with base a, we similarly define a base for the logarithm that works very similarly as the base for exponentials does. If we want to solve these, and we say we have some y value for log base a of x, we can say that y equals log base a of x if and only if we can move the log to the other side to cancel it out, and instead say that x is equal to a to the power y. So the base of the logarithm moves to the other side and becomes the base of the exponential. So in order to evaluate a logarithm, we must undo it and turn the problem into an exponential based problem. which we know how to solve. So let's see this in practice. Let's evaluate log base 2 of 8 and see how we can use this highlighted part in green to solve these. Now let's say I knew what the answer was and I said, okay, y is equal to log base 2 of 8. And if this is true, that means that I should be able to move the base of my logarithm to the other side and make it an exponential. So now the log cancels out, becomes an exponential on the other side, and whatever's inside the parentheses gets free. So 2 to what power is equal to 8? In order to solve this, we need to think and sort of guess and check. Well, 2 to the power 1 is 2. 2 squared is 4. 2 cubed is 8. So y is equal to 3. We have to guess and check and sort of solve for y slowly to figure out what it is. Let's do another one. Let's evaluate log base 10 over 100. We always set these up the same way, and we have some mystery y is equal to log base 10 of 100. We look at the base of the logarithm. We cancel it out by moving it to the other side, and now this becomes an exponential. 10 to the power y is equal to 100. And what should y be? Well, 10 to the power 1 is equal to 10. 10 squared is equal to 100. So y must be equal to 2. Again, we have to play a little bit of guess and check to try to solve these, and there's no other way to do it that we know right now. Our last one will be log base 3 of 1 over 9. Again, the same setup. Then we cancel out the logarithm by moving the base to the other side. 3 to the power y is equal to 1/9. Well, we're not quite sure what this is going to be because turning 3 into a fraction seems a little bit difficult. But from our rules of exponentials, we can simplify this and move the 9 into the numerator by saying that this is 9 to the power -1. Okay, now this seems more doable. Let's see how we can relate 3 and 9. Well, 3 squared is equal to 9. So this means that 3 to the power y should be 3 squared to the power -1. But we know how to combine the 2 and the -1 in this case from our rules. All we have to do is take these two numbers here, 2 and -1, and multiply them to simplify it down to one term. 3 to the power y is equal to 3 to the -2nd power. So therefore, y is equal to -2, and we've solved it. Again, we can check quickly by plugging -2 in for y here, which is 1 over 3 squared, which is 1/9, so we're good. Now we were able to solve these because the number on the base was very closely related to the number inside the parentheses. And the only time we can do these by hand is when this is the case. When we have 10 to some nice power equals 100, or 3 to some nice power equals 1/9. For most cases, however, we need a calculator to evaluate logarithms, and we'll see more often than not, we'll need a calculator to do any sort of complex arithmetic. But actually graphing these turns out to be fairly simple, and we'll see that in the next lecture.